Welcome to Organic Chemistry. Today we are going to explore the preparation of alkanes. These are the sturdy, unreactive, foundational molecules of organic chemistry. Understanding how to build them is your first major step into the world of chemical synthesis, and it will set the stage for everything else we learn. Before we build them, let us understand what alkanes are and why they matter. Alkanes are the simplest type of organic molecules, consisting entirely of carbon and hydrogen atoms connected by single bonds. You can think of them as the sturdy, unreactive brick walls of organic chemistry. Because they are so incredibly stable, they make excellent fuels, such as propane for grills and octane for cars. To build these molecules in a laboratory, we use specific chemical reactions to add pieces, stitch chains together, or chop pieces off. Now that we know what alkanes are, let us look at our first method to make them, called catalytic hydrogenation. Imagine a bus that has several empty seats available for passengers. In organic chemistry, molecules with double or triple bonds, known as alkenes and alkynes, are exactly like that bus. We can fill those empty seats by adding hydrogen atoms to the molecule. However, hydrogen gas is very stable and will not react on its own. We need a conductor, a metal catalyst like platinum, to force the passengers into the seats. This concept leads us directly to the chemical equation for catalytic hydrogenation. The formula shows an alkene reacting with hydrogen gas over a platinum catalyst. The symbols R and R' represent generic carbon chains attached to the central double bond. H2 represents a molecule of hydrogen gas, and PT stands for the platinum catalyst. When the reaction occurs, the double bond breaks open and two hydrogen atoms attach to the carbons. If you increase the amount of hydrogen gas, more of the reactive alkene will be converted into the stable alkane product. Now that we have used this formula, let us understand the three-dimensional geometry behind it. When we add hydrogen to a double bond, we must consider stereochemistry, which is the study of how atoms are arranged in physical space. In catalytic hydrogenation, both hydrogen atoms attach to the exact same side or face of the double bond. This specific type of attachment is called syn addition. You can picture this like two people getting into a car simultaneously through the exact same side door, rather than entering from opposite sides of the vehicle. Let us visualize exactly how this syn addition happens on the metal surface. In this diagram, the flat grey block at the bottom represents the solid metal catalyst. Notice how the surface holds the two hydrogen atoms flat against it, waiting for the alkene to approach. When the alkene molecule, shown above with its double bond, lands on the metal surface, it can only touch the hydrogens with its bottom face. Therefore, both hydrogen atoms are forced to bond to that exact same face simultaneously, completely preventing attachment from opposite sides. Adding hydrogen is great, but what if we want to stitch two smaller carbon chains together? This brings us to the Wurtz reaction. Think of this method like taking two identical Lego blocks and snapping them together to make a single block that is twice as long. It is the perfect tool for making symmetrical alkanes. We start with an alkyl halide, which is a carbon chain attached to a halogen atom, like chlorine or bromine. We then react this molecule with pure sodium metal in a solvent called dry ether. Let us look at the general chemical equation for this stitching process. The formula shows two molecules of an alkyl halide reacting with two atoms of sodium. The symbol R stands for the carbon chain and X represents the halogen atom. Ne represents sodium metal, which is highly reactive and strongly attracted to halogens. The sodium atoms aggressively pull the halogen atoms away, forming a salt. This leaves behind two unstable carbon chains that immediately bond to each other to form the new, longer, symmetrical alkane. Increasing the sodium speeds up the reaction. Before we move on, let us see this with a concrete example. Suppose you are asked to prepare butane, which has the chemical formula C4H10, starting from an appropriate alkyl halide. We know butane is a symmetrical molecule containing 4 carbon atoms in a straight chain. Because it is symmetrical, the Woods reaction is the perfect tool for the job. We just need to cut the target molecule in half to figure out which starting material to use. Cutting a 4-carbon chain in half gives us a 2-carbon ethyl group. Continuing with our synthesis, we now perform the actual reaction. Since we need an ethyl group, our starting material must be ethyl chloride. We react 2 molecules of ethyl chloride with 2 atoms of sodium metal in dry ether. The sodium atoms pull the chlorine atoms away to form ordinary table salt. The 2 remaining ethyl groups immediately crash into each other, forming a new carbon-carbon bond. This stitches the 2 halves together, giving us our final product, butane. This method efficiently builds any alkane with an even number of carbons. While the Wurtz reaction is powerful, things do not always go perfectly according to plan. Sometimes a completely different reaction called competitive elimination happens instead. Elimination is a process where atoms are stripped away from a molecule, causing a double bond to form instead of the desired single bonds. This usually happens because of steric hindrance, which means the carbon chain is too bulky and crowded. When the molecule is too crowded, the reagents cannot reach the carbon atom to stitch the chains together, so they just rip a hydrogen atom off the edge instead. Since building larger molecules can sometimes fail due to crowding, another approach is to take a large molecule and chop a piece off. This process is called decarboxylation. Decarboxylation literally means removing a carbon atom and 2 oxygen atoms from a molecule in the form of carbon dioxide gas. We do this by taking a salt of a carboxylic acid and heating it with a harsh chemical mixture called soda lime. You can imagine this process like trimming the crust off a sandwich to leave only the soft center behind. Let us look at the chemical equation for this chopping process. The formula shows a carboxylic acid salt reacting with sodium hydroxide under strong heat. RCOONA is the sodium salt, where R is the carbon chain we want to keep. NaOH represents sodium hydroxide, the active ingredient in soda lime. The triangle symbol over the arrow indicates that strong heat must be applied. The heat causes the entire tail to break off and combine with the sodium hydroxide, leaving the R group to pick up a hydrogen and become our alkene. Let us apply this new method to synthesize the simplest possible alkane. Suppose you need to prepare methane, which has the formula CH4 starting from sodium acetate. Methane contains only 1 carbon atom, but our starting material sodium acetate contains 2 carbon atoms. This means we need a reaction that destroys exactly 1 carbon atom from the starting material. Decarboxylation is the ideal method here because it specifically chops off 1 carbon atom in the form of a carbonate group. Now we will execute the reaction to get our final product. We mix solid sodium acetate with solid soda lime in a test tube and apply strong heat using a Bunsen burner. The sodium hydroxide attacks the molecule and the entire carboxylate group is ripped away from the methyl group. The methyl group immediately grabs a hydrogen atom to stabilize itself. This forms CH4, which is methane gas that bubbles out of the mixture, leaving behind a solid white powder of sodium carbonate. We have successfully synthesized methane. Now that we know how to make these molecules, we must ask why they are so important in the real world. Understanding how to prepare alkanes is absolutely critical for modern industry and daily life. Alkanes are the primary components of fossil fuels, including natural gas, gasoline, and diesel. Without these synthesis methods, we could not create specialized fuels or high-quality lubricating oils. Furthermore, alkanes serve as the foundational building blocks for creating plastics, synthetic fibers, and pharmaceuticals. The entire chemical manufacturing industry relies on these simple carbon chains. We have covered a lot of ground today, so let us review the most important ideas. The preparation of alkanes involves transforming other organic molecules into stable, single-bonded carbon chains. We can achieve this by adding hydrogen to double bonds through catalytic hydrogenation, coupling smaller chains together using the Wurtz reaction, or removing carbon atoms through decarboxylation. The specific method you choose depends entirely on the size and symmetry of your desired final product. Mastering these basic reactions provides the foundation for understanding all complex organic synthesis.